All right, everybody, this is part 2 of, I guess, lecture on 10.4. I'm going to try to go through again some of this stuff pretty quickly. Things I would have done before on the board, I'm just going to kind of talk about briefly. But hopefully if you have any questions, you'll be able to ask me on Wednesday at our next class period. So continuing with a few properties of the cross product, this is called Lagrange's identity. It demonstrates the relationship between cross products and dot products. So again, you have to have vectors in R3 or the cross product does not even make sense. And here you can see the identity credited to Lagrange. So if you take the cross product of u and v, find the magnitude of that new vector and square it, it's the same as if you had squared the magnitude of u, squared the magnitude of v, multiplied them together, and then subtracted the dot product of the two vectors squared. So now that's going to show up here in a minute or so. We're going to see how that's used again. And then it turns out that the vector produced by the cross product of the two other vectors is orthogonal to both original vectors. Remember, orthogonal is one of those fancy words for perpendicular, also normal. So if you have u and v as vectors in R3, then the dot product of u with the cross product of u and v is 0. And if you dot v with the cross product of u and v, you also get 0. Notice that is the scalar 0, not a 0 vector, because the end result is a dot product, and a dot product is a scalar. And as we learned earlier, that if two vectors are perpendicular to each other, their dot product is 0. Okay, so the magnitude of the cross product is somehow related to the magnitudes of the angles between them, and here's the relationship that our book gives us. The magnitude of, can't find my mouse again, it disappears every now and then. The magnitude of the cross product of u and v is equal to the magnitude of u times the magnitude of v times the sine of the angle between them. This is if you put both vectors on the same set of coordinate axes where they share the same initial point. And theta here is the angle between u and v. So because this is true, you know what? This is the proof of the last theorem right here, and this proof is pretty understandable, and we use Lagrange's identity from before, which I did not explain, to prove this. But this is a very useful result because it helps us find area here in just a moment. So by Lagrange's theorem, we had this first statement, so this was several slides ago. This magnitude of the cross product squared is equal to the magnitude of each of the individual vectors squared minus the dot product squared. Well, if you just play around with the right hand side here, do a little bit of algebra, the results of this new theorem just falls right out. Remember that the dot product of u and v was also equal to the magnitude of u times the magnitude of v times cosine theta. So I'm just making that substitution here. And then if you notice, there's two terms on the right hand side, this term and this term. If you square this out, they'll both have a magnitude of u squared and a magnitude of v squared. So in this line, I'm factoring that magnitude of u squared and magnitude of v squared out. That leaves a 1 in this first term, and you're left with cosine squared theta here, and bring down the minus sign. And 1 minus cosine squared theta by a Pythagorean identity is sine squared theta. And so we have this expression squared equals this expression squared. And if you take the square root of both sides, we do arrive at this expression right here. So Lagrange's identity is used to prove that one. And now we can say that two non-parallel vectors end up determining a parallelogram, and the area of that parallelogram is given by the magnitude of u times the magnitude of v times sine of theta. So if you see we have v here and u here, you can use a little right triangle trigonometry to get that this height should be, the sine of theta would be opposite over hypotenuse. Hypotenuse is going to be magnitude of v. So if you solve for the opposite side, you get magnitude of v times sine of theta. And you may or may not recall, but the area of a parallelogram is given by height times base. So this is the height, this is the vector base, but the length is the magnitude of it. So we get magnitude of u times magnitude of v times sine theta. But from our previous theorem, we know that this expression is equal to the magnitude of the cross product of u and v. So if you want to find the area of a parallelogram whose two sides are given by vector u and v, you can simply find the magnitude of the cross product of those two vectors. It's kind of a cool result. And that's something that you have to do on the worksheet for 10.4. Alright, three vectors u, v, and w that cannot be translated into the same plane are said to form a right-handed triple if, when the index finger of the right hand points in the direction of u and the middle finger of the right hand points in the direction of v, then the right thumb will naturally point in the direction of w. So here's the I guess geometric representation of that. If you imagine putting your index finger in this direction and your thumb in this, your index finger in the direction of u and your middle finger in the direction of v, your thumb will point in this direction, assuming you're using your right hand. And that tells us the direction in which u cross v points. So it turns out that u, v, and the vector u cross v always form a right-handed triple in R3. So a few more properties of the cross product here. If u and v are parallel, then the cross product ends up being 0. You can try that out with two vectors and see if that's true. If u and v are not parallel, then u cross v has these following properties. The cross product is equal, the magnitude of the cross product is equal to the magnitude of u, magnitude of v times cosine theta, or u cross v is perpendicular to any plane containing u and v. You can kind of see that here too, that u cross v is perpendicular to both u and v. And uv and u cross v form a right-handed triple. So this is like the third problem on 10.4, which I originally did not want you to do, but now I do want you to work on that. I'll put that in my announcement as well. That if you have 3 points here, we're going to find several things about them. We're going to find a non-zero vector n, and we're calling it n for normal, perpendicular to the plane, determined by those points. 2 unit vectors perpendicular to the plane, determined by those 3 points. And then the area of the triangle determined by those 3 points. Let's see if I can somehow, there we go, make it advance. Okay, we can get our normal vector basically by creating 2 vectors in the plane and then crossing them together, because that new vector will have to be perpendicular to the original plane. So I form PQ and PR here. Remember how to form those. PQ is just 0 minus 3, 6 minus 1, and negative 1 minus 8. And then PR, similar process. And if we compute the cross product for those two, we will get a perpendicular vector. So here's PQ cross PR. Notice I put PR first and PQ first and PR second, because that's the order I did the cross product in. And I've skipped all the steps here, but if you go back and verify, you should be able to get negative 19, 21, and 18. And this vector will be perpendicular to the original plane. The second part was we were wanting to get 2 unit vectors that were perpendicular to the plane. Well, the way we can get those 2 unit vectors is to have one pointing up and one pointing down, both of which would be perpendicular to the plane. But in both cases, we need to know the magnitude of that cross product. So we do a magnitude calculation. Since we had the magnitude from the previous slide was negative 19, 21, 18, we just square each of those components, add them up, take the square root. So I get square root of 1126. So 1 over the square root of 1126 times our cross product is one of the unit vectors, and then negative 1 over the square root of 1126 times our cross product is the other unit vector. They're pointing in opposite directions, but both of them are exactly perpendicular to the plane containing those 3 points. And the last piece of this was to determine the area of the triangle determined by the points. Again, if I had the board, I could do this better, but a triangle is exactly half of a parallelogram. So since we know the area of a parallelogram formed by PQ and PR is simply the magnitude of the cross product of U and V, then the area of the triangle formed by those 3 points is just going to be 1/2 of that magnitude. So the magnitude is the square root of 1126, so square root of 1126 over 2 is going to be the area of the triangle. And lastly, let's talk about the parallelohyped. This is the three-dimensional analog of the parallelogram. So if you extended a parallelogram into a third dimension, we have this new fun term, parallelohyped. The triple scalar product is what is used to find the volume of it. So if you have three vectors u, v, and w, the absolute value of u dotted with the cross product in v of v and w is the volume of that parallelohyped. And the volume of the parallelohyped is that if and only if u, v, and w form a right-handed triple. So you don't have to worry about the absolute value signs if you do have a right-handed triple. And the triple scalar product is equal to 0 if and only if the three vectors are coplanar, which would make sense if your three vectors are all in the same plane. They don't actually form a parallelohyped, so you can't find the volume of it. Here's a few more properties of the triple scalar product. You can move around the order in which you do the dot product and the cross product. Though you see here we have u, v, w. You still have that same order here. It's just like you shifted everything. So if you have u, v, w, and over here you still have u, v, w. So as long as you keep them in the order u, v, w, you can move them through. And here we have the u dotted with v cross w is the same thing as u cross v dotted with w. So that's interesting too. You can interchange the dot and the cross as long as you do the cross first in both cases. And I am going to skip the true-false. It's kind of anticlimactic to do via a I guess video lecture here. So hopefully that helps you better understand some of the material in 10.4. I'm going to try on Wednesday to go into 10.5, and we'll talk about lines and planes and how they're defined in space. I'll also take questions on the material from 10.4 or before, and you can also send me any email questions if you have any. Hope the rest of your snow day goes well, and I'll plan to see you Wednesday. Thanks.